Hello, how are we? Our aim says how to evaluate limits of piecewise functions. My goal for this video is to get you to solve problems like this, where you're given a piecewise function and you're asked to evaluate the limit as x approaches some value in that piecewise. But before I get there, just some quick review. For the do now, I'm asking you to evaluate each limit and justify your answer. Remember that to answer these questions, you need to know your horizontal asymptote rules. So let me just put them down real quick. So n greater than m, that's no horizontal asymptote. Okay, so for number 1, we have do not exist. For number 2, we have 19 over 47. And for number 3, we have 0. And let me just give a quick justification for each one. So for number 1, you could see right here that the degree in the numerator is less than the highest degree in the denominator, so I'm using the third rule here. For letter B, the degrees are the same here, so I'm using the second rule. And then for letter C, you can see that the degree in the denominator is larger than the degree in the numerator, so I'm using rule number 1. Okay, so that's that. Letters A, B, C, and D. It says, what do you know about the graph if given the following information? So for letter A, I'm told that the limit as x approaches 4 of the graph of f is equal to 7. So, okay, so what do I know about the graph? Well, if all I'm given is the limit, all I know is that the intended height of the graph is 7 as x approaches 4. So the graph could potentially look like that, right? Because the intended height is 7. Or it could look like that. So you could have a hole there, or maybe you don't have a hole there. Okay, so these are just potential scenarios. Of course, there's a million other, these are just potential scenarios. There's a million other scenarios you could come up with. I'm not saying the graph looks like this. It could potentially look like this. Letter B, we're told the limit as x approaches infinity of f is equal to 0, then that means you must have a horizontal asymptote at y equals 0. So now look at letter C. So letter C says the limit as x approaches 1 of f is equal to negative infinity. So then in this case, right, where the limit is equal to an infinity, then that's indicating that there's a vertical asymptote. So this is saying we have a vertical asymptote at x equals 1. So what could that graph look like potentially, right? It could potentially look like something like that. Right, so as x approaches 1, the graph goes down to negative infinity. Okay, last one, letter D. So this is telling us the intended height of the function is equal to 4. So this speaks to intended height, but then this speaks to a point, right? So this is saying the intended height of the function as x approaches 1 is equal to 4, but then this is saying we have a point at 1, 6. So the graph could potentially look something like that, right? Where the intended height is equal to 4, but we have a point at 1, 6. Okay? Alrighty then. So, okay, so for the next part, we are given a piecewise function, and you're being asked, what do the following limits appear to be? So for letter A, what's the limit as x approaches infinity, right? So if I could keep extending this graph more and more, what do you surmise this graph would keep doing? Well, I say that the graph would be approaching this value of 4, right? You could see how it's doing this little squiggly thing, right? It just keeps squiggling around, but eventually it just keeps squiggling around that line y equals 4. So that's indicating that we have a horizontal asymptote at y equals 4. Now, I know what you're thinking. How could we have a horizontal asymptote there if the graph crosses it? And we addressed this earlier in the year, and we said that it is possible for a graph, in some cases, to cross the horizontal asymptote. And what I would encourage you to do, if you have some extra time, look at the graph of the sine of x over x. Take a look at that graph. You will actually see that the limit as x approaches infinity of this graph is equal to 0. And it starts behaving in a similar fashion to what we just saw. Okay, so this is extra, right? If you have time, take a look at that graph. Okay, let's move on. Letter B. What's the limit as x approaches 1 from the positive side? So then let's go ahead and find that. So as x approaches 1 from the positive side, that will be negative infinity, right? So as x approaches 1 from the positive side, right, from the right side, it goes down to negative infinity. What's the limit as x approaches negative infinity, right? So now we're asking, if we kept going that way, right, if we kept going all the way to the left, what would the graph do? And then you would see that the graph would eventually just get closer and closer to this horizontal asymptote, but it would never actually reach it, so that limit is 2. Since it is a piecewise function, it's okay that we have 2 horizontal asymptotes here. The piecewise indicates that that is a possibility. Letter D, as x approaches 3 from the left side. So as x approaches 3, here is 3. From the left side, we get 6 is the intended height. Now we're going to do 1, and we're going to do 1 from the left side as well. That is positive infinity. Now 3 from the right side, the limit is 2. And then what's the limit as x approaches 0? So here is 0, the intended height is 4. Alrighty then. So what I want us to answer today is this question right here at the bottom. What if you are only given a piecewise function without the graph? How do we find the limits now? So let's turn the paper to the back. And I'm going to work out an example with you. Okay, so pay close attention, right? Because this is the aim for today, right? How do you solve these types of piecewise functions? So what you want to do is you want to take the limit at 4 from the left side and from the right side. So then let me plug 4 into this function right here. So then that's going to be 8 minus 2 times 4, which is 0. I plugged it into this one because this is the function that I should use for when x is less than 4, right? And I'm coming at it from the left. So then it says, what's the limit of f as x approaches 4 from the right? So now you use the top function, and then you're going to get the same thing, 0. So since the limit from the left is the same as the limit from the right, then the limit of f as x approaches 4 is 0. Okay, so try the next one on your own and then come back and finish the rest of the video. Okay, so for number 1, it says the limit as x approaches 2 from the left. So I need to use this function at the top. So I'm going to plug in 2 and I get 6. For number 2, it says find the limit as x approaches 2 from the right. So as x approaches 2 from the right, I'm going to use the second function. You should get 4. Okay, so number 3 says find the limit as x approaches 5. So I have to find the limit from the left-hand side and the right-hand side. So please keep that in mind, right? So in order for you to do that question right there, number 3, you have to first do the limit as x approaches 5 from the left. Then you have to do as x approaches 5 from the right. And you have to make sure that they're equal. So let's plug into the top one. If you plug into the top one, you get 7. And if you plug into the bottom one, you also get 7. So then that limit is 7. But just make sure, right, that you check. Don't just plug into one of them. You got to check from the left-hand side and the right-hand side. And then the last one says find the limit as x approaches 2. So again, in order for you to find this limit, you got to do the left-hand side, which we already did, and the right-hand side, which we already did. And you're going to see right there that the two limits are not the same. So this limit does not exist. Let me just show you the graph to this real quick. That's not it. This is it. Okay, so you could see here, we're given the graphs. Let me just move this up a little bit. So this pink line is x plus 4, right? So use this line for when x is less than 2. And then we got this parabola here from 2 to 5. And then we got another line here when x is greater than 5. So now you could see clearly, right, when x is equal to 2. So here is x equals 2. You could see that those two heights don't match up. So that's why that actually proves what the algebraic work we just did. But then you could see here that as x approaches 5, those heights do match, right? The left-hand limit and the right-hand limit is the same, and we have an intended height of 7. Okay, so extra limit practice. So hopefully for number 1, you tried direct substitution first, and you got -2. For number 2, if you tried direct substitution, you got 0 over 0, which means that you have a whole, so we have to conjugate. So let's go ahead and conjugate rad x plus 5 plus 3 over rad x plus 5 plus 3. Let's go ahead and multiply this out. So this is multiplication, all right? We're multiplying that way. So in the bottom, I'm going to get x minus 4 times rad x plus 5 plus 3. And then in the top, rad x plus 5 times rad x plus 5. Well, that's just x plus 5. And then -3 times +3 is -9. So then I'm going to have this 5 minus 9, that's -4. So then you can see how that's going to cancel out with that one. And then here I have rad x plus 5 plus 3. So these cancel. So I get 1 over rad x plus 5 plus 3. Let's go ahead and substitute 4 plus 5 plus 3. So then that's going to be 1 over 3 plus 3. So I get 1/6. Okay, so for number 3, if you tried direct substitution, you got 0 over 0, which means there's a whole, so we have to factor. So factor the top, x minus 4 times x plus 3, factor the bottom. These cancel out, plug in 4, you get 7. Last one, this is saying the limit as x approaches infinity, so this is asking for a horizontal asymptote, so use those rules. So you could see here that the degree of the numerator is greater than the degree in the denominator, so we get does not exist. Okay, I hope this helps. Take care.